ladder logic timers. We're going to look at problem 10 in the workbook. We might sequence through a couple more of them. This one gives us a ladder logic timing diagram, or not a timing diagram, but a ladder logic diagram here with several parts. And the question just basically says, how does it work? So let's look at it and see if we can figure out what we have and what controls it. Okay, sometimes what I like to do, especially if I have colored pencils, is I'll look at CR1, this coil here, and I'll establish that it controls that set of contacts. Okay, TD1 controls that timer. Okay, this right here is an overload relay. For the motor. Maybe. I don't know, you tell me. It might not be an let's belay that for a minute, because it looks to me like we have an overload relay up here. And notice it's in between L2 and the connection point for all the loads. So that basically disables the entire circuit if that goes down. Okay, so let's look at this and see what happens. Evidently, there's a time delay involved. What kind of time delay is this? It looks like this. And as such would be which type? Normally
open, timed closed.
Timed closed. So what it will do is when the coil, or TD1, gets its signal, it will wait a certain amount of time, delta T, before it turns on. And that would be the motor. So motor M1 turns on a certain amount of time, whatever this is set, let's just say that it's set to n seconds. Motor will come on n seconds after that coil is energized. What do we need to do in order to energize that coil? Well, what happens if we press the start button? If we press the start button, that allows energy to flow to this coil. And when energy flows to that coil, it closes that set of contacts. Once that set of contacts is closed, we can let up on the start button, because we've latched that start using that contact. And even though we've let up on the start button, now the energy will flow in this direction through the closed relay, and it will continue to flow that way until which point we press the stop button. When we press the stop button, that will take the energy away from CR1, and the contact associated with it will open back up again. Okay? What else is going to happen? As soon as we press that start button starts the timer. So TD1 here could also be called start. As soon as the start button is pressed, it's latched here, the timer starts. When the timer starts, what happens? The contactor for M1 turns on. So here, the motor of course, turns on with TD1. Now, what's the story with M1 and the siren? What's going on here? Can you figure out what's that siren all about? When is the siren on?
After the start button is pushed.
What conditions have to exist for the siren to be on? One, the start button or CR1
Yes.
have to be on. So I'm just going to call that start on, and we'll just put CR1 in parentheses so that we know that the start or CR1 has to happen. That gives us energy to the siren, but only if the motor contact is closed. That motor contact is normally closed, which means that the siren will be on when the motor itself is off. As soon as we turn the motor on, in other words, as soon as the timer is expired, the motor turns on, this thing goes away, and the siren turns off. So when is the siren on? The siren is on during this time. Okay, what's going on during that time?
Oh, the delay for the motor start.
The delay for the motor start. So what the siren does is it enunciates to anyone who cares that
The motor is
hey,
starting up.
the motor is getting ready to start. It's not moving right now, but get the hell away from it because it's just about to start up. Okay, and then we'll go until the motor starts. Once the motor starts, the siren turns off. The motor will continue to run until one of two things happens. What two things can cause the motor to turn off? What two things can cause the motor to turn off?
The overload and the stop.
The overload, if the overload goes, no current flows through the system because it all has to go through the overload relay. So if the overload relay opens, that's dependent on the motor. The motor circuit controls that. The protection of the motor senses too much heat in the motor itself as it's running and will break that connection. So this is a heat sensitive connection here that determines if the motor is over-temped. If it is, then everything shuts down. If that happens, there's no siren, there's no motor. If the stop button is pressed, what happens if the stop button is pressed? Well, that's going to happen right here. Let's say it happens right there. Everything turns off when the stop button is pressed. As soon as the stop button is pressed, it breaks all of this, and we go back to our initial situation, which is the siren is connected to the power supply, it's ready, but there's no power to it until we push the start button. The CR1, TD1 are both all ready, but there's nothing going to it until we press that start button. Once we press that start button, the entire process starts again. Okay? So this is a system that allows you to start a motor with a 4-second delay, and then that motor will continue to run until the stop button is pressed. In the meantime, the time between when the start button is pressed and this delay expires, there'll be a siren that goes off to indicate that the motor is just about to fire up. Okay, does that make sense how that works? So that's a nice little example.
Exactly the same as the last one, except the motor 1 turns on before motor 2.
Yes, that's what it seems. Let's see if we can figure out what goes on here. It does, it's very similar, and you'll find that a lot of ladder logic programs do have similar elements. For example, the latching relay, that's pretty common. Same thing is true here. CR1 controls CR1. TD1 controls TD1, M1 and M2 control their respective motors. This here controls that.
Oh.
See, that might be the part that you missed.
Yeah, that
So, press start. What happens when we press start? When we press start, this gets energized, that energizes this, and energizes this. So as soon as we press start, N seconds starts. Right?
Yeah.
What else happens? When we press start now, M1 turns on. What happens when N seconds ends? M2 comes on and M1 comes off. As soon as this becomes on, M2 turns on, but M2's contact also opens here, breaking this and turning M1 off. Press start right here. M1 turns on right then. M2 comes on N seconds later, and when it comes on, M1 turns off. When the stop command is issued, everybody shuts down. Questions?
No, it's
Pretty straightforward and simple, isn't it? That's the beauty of ladder logic, and that's the reason that we still use ladder logic to program PLCs, because it's so easy to understand and so easy to implement. As you see when we look at these boards, hello. Most of the time, you know, when we look at these boards like this, everything's wired up into down here, but you have your contactors and timers down on a row here and switches over here. It makes it really easy to just be able to lay this out. what we do is we give the individual wires numbers, and then in the real world, we label the wires with those numbers on our connections, so that anybody can come in off the street and be able to figure out what's going on. Not that that's the best way to run a business, but people do that sometimes. Okay, before we move on to the next, I want to look at this drawing that's right underneath this example, which is a motor protection circuit. Okay, here you have contactors that are used to turn the motor on. In this case, M2 and M1 control the same motor. You see that? It's the same situation. There is, however, one difference between these two. This says R. What does R mean? When you see something that is a squiggly line that has an R next to it, what does it generally mean?
I would say resistor.
A resistance. Okay? Here's what we are doing. When we look at both parts of this, it makes a little more sense as to what's happening. We turn on M1 first, right? That's right here. That sends the current through the resistance and starts the motor off slowly. Then, after a certain amount of time, we switch over, we break M1, and we connect M2 together, which now sends the power to the motor with no resistance. Okay, so what this is startup and run. So when you look at both parts of this together, this doesn't make much sense without the schematic, and the schematic doesn't make much sense without this. Okay, so what this is a soft start circuit that uses two sets of contactors to step up the speed of a motor, starting out with a slower speed through resistance, then moving to a faster speed with no resistance. Notice that there is overload connections here, and these are connected directly to your three-phase power source. Okay? Questions on that? You want to look at the top diagram again? Otherwise, we'll move on to one more example. Move on to one more example?
Yes, please. Is that okay with you?
Yeah, that's right.
Put up an easy one. There's a timing diagram. Question in the book says, an engineer brings you this timing diagram and says, I want you to design a circuit that does that for me. And the technician looks at it and says, ha ha, or does what they actually talk about, LOL, laughs out loud. Why is the guy laughing and saying, you can't do that? What's wrong with that? This one. It's question 13. So it's unlucky. What's wrong with that timing diagram? Push button, lamp. See anything funny about that?
I'd say it's too simple.
Is it?
Just my opinion.
All right, here, let me put this into another example that will make it obvious. Okay? Sometime in the next 40 years, this is today, this is 40 years from now, what would that be? 2055, I will be what? 97 by then. Somewhere between now and 2055, I'm going to die, most likely. 1 month before that happens, I would like you to buy me flowers.
Before you die.
Right? Well, that's what we're saying. Here's the push button. I want the light to come on X amount of time before I let that push button up. Right? How can you possibly expect to create a circuit that predicts the future? And that's what you're expecting here. You're expecting the response to come before the stimulus.
Okay, what's wrong?
Now, is that to say that that couldn't be done? Well, in a sense it could, because we're looking at this time. But if we were looking at this time, then we could simply use an on delay timer to do that. But I'm not representing this as I want this to happen X amount of time after that fact. I'm representing that I want it to happen X amount of time before the next event. That's the way this is drawn. Okay, it's one thing to say I want this to happen 6 months from now, but it's another thing to say I want it to happen 2 months before some event that may or may not happen in the future. Do you see that? You see that, Mr. Bell? You see why that's
I see it now, yes.
that's a problem? We can't predict the future, so
No, you can't.
you know, we cannot draw timing diagrams that depend on some future event. It's always cause and effect. One comes before the other. The effect never comes before the cause. Okay? So that's kind of a fun example. We'll pick a few more of these. Obviously, we haven't done a whole bunch of them, so there's a lot of them in here. I hope you've downloaded this and looked at it at least a few times. All of these are kind of interesting, and they all require you to think. So analyzing these is a great way to get ready for when the timers actually show up and we can start hooking them up to that board.
Okay.
Okay? Questions?